Hello, Akshay.
Hello.
Hello,
Hello. Good evening, Mani.
Akshay.
Yes, sir. Hello.
Hello.
Good evening, everybody. We are just waiting for the speaker and we'll start soon.
Okay.
Hello. Hello.
की आवाज आएगी। आवाज भी बंद कर।
Hello, everybody.
Yeah, hi Abhi.
Welcome to the webinar. This is Kushagra. Thank you for
Hey,
being here.
Kushagra.
I'll just. So, are we ready to start, or do you need some time to settle in?
I'm ready. If everybody's online and we're good to go whenever.
Yeah, I think we're all ready. We already have 87 participants, which is great. I
Awesome.
think the webinar was supposed to start at 17:30 hours, but it's 17:24 right now. And
Okay.
we're already 55 people. So thank you everybody for such an encouraging response. This is a webinar by the two young chapters of ASHRAE, ASHRAE Chandigarh and ASHRAE Rajasthan. Both the chapters are formed very recently. ASHRAE Chandigarh has done a webinar before as well. This is the first joint webinar of both the chapters. The response is truly encouraging. I am Kushagra. I am the YEA chair for Rajasthan chapter, and even from Chandigarh chapter, we are joined by Mani and the YEA chair of the Chandigarh chapter. To quickly introduce the topic for today would be high levels of the controls 101, which will help us gain an understanding of the building automation systems and its fundamentals alongside moving pieces which are involved in a typical building automation systems project. So I'll hand it over without taking much time to Abhishek. I would request all of you to kindly mute your mics, and we will take questions through chat. And Abhishek, you can call out for questions whenever you're ready.
Okay, great. Will you be driving the slides, or can I get the? Can I share my screen?
Yeah, Abhi. Yeah, Abhi. Just
we can drive the slides.
Hello.
Yeah, we can drive the slides.
No, but
you don't have the latest set of slides that I have.
Okay. Okay.
Yeah. Before start with the presentation, I would like to request Mr. Akshay Kumar to speak a few words before starting. He's also YA chair of Chandigarh chapter.
Thank you. Am I audible?
Yes, you are audible. Yeah.
Hello everyone, I am Akshay Kumar, YA Chair, ASHRAE Chandigarh Chapter. Welcome to this webinar organized by ASHRAE Chandigarh Chapter and ASHRAE Rajasthan Chapter. I am sure you all are aware about ASHRAE. ASHRAE is the American Society of Heating, Ventilation. Hello?
Yeah, please speak. Yeah.
ASHRAE is a society of heating, refrigeration, and air conditioning engineers with the mission to serve humanity by advancing art and science of HVAC-R and their allied field. The society consists all the professionals members related to HVAC and building industries. ASHRAE Chandigarh chapter has taken initiative to spread knowledge among the members. We scheduled series of webinars in this month. During the lockdown period, today is our fourth webinar on topic Control 101. This topic will help you gain an understanding of the building automation system fundamentals alongside the moving pieces which are involved in typical BAS projects. To go through with activities done by ASHRAE Chandigarh chapter. If you are ASHRAE member, then it's fine. If you are not, then be a part in ASHRAE Chandigarh chapter by register online at join.ashrae.org. I thank to our sponsors. It's truly meant too much to us. We have two annual technology partners, Armacell and Flowguard Blaze Master, and 5 annual partners, Aralom, MaxFlow, Jivandeep Enterprises, Matter Joints, and GL Enterprises. Now, I would like to introduce today's presenter, Mr. Abhishek Khurana. He is the CEO of Viker Buildings, a BAS contracting firm based in Toronto, Canada. Mr. Abhishek has extensive experience in new construction, installation, and existing buildings retrofits. He is also a big advocate of leveraging artificial intelligence alongside automation system to reduce our building carbon footprints and operation costs over the years. Abhishek has also had various roles at ASHRAE Toronto and is currently the vice president of the chapter. Now, I would like to I request Mr. Abhi Khurana to start this webinar.
Awesome. Thank you for the introduction. So if I could get the screen control here. Great. Let me know when you guys can see my screen.
Yeah.
All good? Okay.
Yeah, good to go.
All right. Well, thank you everybody for having me here. First of all, I would like to say that this presentation definitely holds a special place in my heart because I am from Chandigarh and I've lived half my life in Chandigarh at this point in time. So again, thanks for having me. I'm very excited to do this. And not to discredit Rajasthan, of course. And it's great that you guys are doing this joint event and you guys are new chapters. And I would like to see how we can explore this relationship further and possibly do more joint events in the future. So without further ado, some of this initial ASHRAE stuff has been covered already, so I will fly through it. So ASHRAE was founded in 1894. We are a fully volunteer organization with over 57,000 volunteers and spread across the globe. This is a great example. Me sitting here in Toronto giving a webinar in Chandigarh in Rajasthan, or possibly more chapters in India. This is a great example for that. So it is primarily focusing on the HVAC and R industry. We did come up with a strategic plan in the 2019-2020 year, which is this year, coming to an end in June, for the next 5 years. I would encourage you to read that strategic plan online if you are interested. It's on ashrae.org/strategic plan. My ASHRAE is the hashtag that is officially being used by all ASHRAE members across the globe. So if you do end up posting anything on any social media, please use the hashtag myASHRAE and you will be, and if you want to search up what other ASHRAE people are up to around the world, you can search the hashtag as well. We also have an app, it's called ASHRAE 365. So it is available on iOS and Android, so feel free to download that as well to get a scoop of what's going on with ASHRAE. Connect a Colleague is a program that was introduced by ASHRAE to help you include people that you work with or people in your industry, in the ASHRAE world. So ASHRAE, if you go to Connect a Colleague page on ASHRAE, all you need to do is just put in their name and email, and ASHRAE sends a pre-written email to them saying you have referred them and you would like to connect them. And again, if you are not a member as originally discussed, please take a look at the membership rates and the benefits that you will receive by being a member, such as these, and highly encourage you to sign up. So today's agenda, Controls 101, we're going to go over some of the history versus the present, how the controls used to be and what they are today, some of the communication protocols, control points, some hierarchy, some optimization strategy, and we'll do a quick sample to see how we get along. And again, I would like this to be a discussion. So if there's any questions at any given point in time, feel free to just let me know and we'll get them addressed as we go along. So starting from the history, back in the day, we had pneumatic systems. So everything was controlled using pressure, which is not the case today, as most of you may know. So there are a lot of problems in pneumatic systems, which is why over the years we've deviated away from them. For example, there's a compressor which is pushing the pressure out to all different parts of the building so the control system can work as required. Now this air dryer, there's this air dryer in there as well, because if the air, so there's an air dryer in there, because if the air that is going through the tubes has a lot of moisture, then we are not going to get the pressure that is required at any given point in the system, and we may not be able. So we may be thinking that we're telling the valve to open 100%, whereas the valve may only be open less than that. Similar thing with the air filter, where now there could be particles that are going through the tube that could cause clogging. So the air filter kind of helps with that. So basically, long story short, you see there's a lot of problems that were with these systems in the past and why we've deviated away from them. Moving on to what we use today, primarily everywhere, electronic systems, or sometimes called DDC systems, where everything is electronic. The signals are sent in the form of 0 to 10 volts or 4 to 12 milliamps, 4 to 20 milliamps. Everything kind of looks like this green circuit board, and it's inside a controller casing. So we'll do an example of pneumatic versus electronic valves. So you can see in this case, the valve's being controlled by pressure. So there's this branch line that we saw in the previous example. The pressure comes, the actuator chamber presses on the diaphragm and the spring, and now slowly the plug starts moving forward down on the valve seat. So the flow of the water is restricted. And this is how the pressure is used to control the pneumatic valve. And now in this case, the actuator sent a 0 to 10 volt signal, for example. And if you say, hey, actuator, this is 50%, it'll just precisely close it by 50%. There are also end devices which we can use on actuator, which basically give us feedback on how much the actuator ended up closing by the end of the motion, and gives us an understanding of the system's flow rate, etc. Communication protocols. So back in the day, again, when everybody was doing automation their own way, every company, all the manufacturers were using their proprietary protocols. Two manufacturers couldn't talk to each other's controllers at the time. And since then, various industry partners have stepped in. There have been more communication protocols that are around today. Initially, we all moved to a protocol called LAWNWorks, or LAWN, you may have heard. And even over the years, ASHRAE has stepped in and said, hey, look, this is what we've been doing with BACnet, and this is going to be the new industry standard. So today, in today's world, any new installation that happens is typically a BACnet communication protocol, and it is the industry standard. If there are any consulting engineers over here, this is typically a stamp that, or BTL is a third party which every manufacturer sends their products to, and they do all the testing. They check for interoperability to see if manufacturer A's product works well with manufacturer B, C, D, and they give them the okay. And on their website, you can see BTL website, you can see all the manufacturers listed, all their products listed, and you can also see how or which products of the manufacturers are approved by BTL, basically. And over here, consulting engineers use the phrasing in their specifications, such as the product supplied by the controls contractor will be BTL tested, something along those lines. So if you're a consulting engineer, this is something you may want to look into. We will go over some sort of basic control points. So on a controller, at the end of the day, it's either an output or an input. Now, if the point is either binary or it's analog. So now we have binary input, binary output, analog input, and analog output. So binary is 0 and 1, so it's on or off. And analog is modulating signal that we are going to look into. So let's do a couple examples. So something like temperature. Now, temperature reading, it can fluctuate. It can go even up or down by decimal points. So at the end of the day, that's going to be an analog signal. Now, it is how you determine if it's an input or an output is because on the controller, the signal is going to go from the sensor to the controller. So the signal is an input in the controller, and hence the signal will be an analog input, a temperature signal, that is. Similar thing with pressure. Now, if we go on to the other end on an analog output signal, that would be something that is a modulating valve. So the controller needs to tell the valve, hey, open up 50%, and that's a signal being sent from the controller to the valve, hence it is an output. So far, so good? I'm gonna take silence as a yes. Something like, let's take a pump for an example. Now, if a pump is just a simple pump without a VFD, then you have two basic points. One is on and off, which is your binary output, binary because it's 0 and 1, and output because it's going from the controller to the pump. And the other one is status, which is basically, we put a current transducer to tell us if there's current flowing through the coil, and it gives us the signal that it is on or off. So from a hierarchy standpoint, we have 3 different levels. So we've got the unit level controls. So basically think about it as this. So any piece of equipment that has its controller is that controller is a unitary controller. So a chiller is going to have a controller, that's a unit level control. A boiler is going to have a controller, that's a unit level control. VAVs, fan coils, air handlers, you name it, every piece of equipment has its own controller, that's a unitary controller. Okay. Now, all these unitary controllers are all around the building, but now you need a central brain to control all the equipment and make it work as a system. So which is why it comes in the system level controller. And there are cases, for example, a university where you may have multiple buildings. Now in that case, you may have something which is an enterprise level, whereas each building may have one or more, depending on how many points there are, system level controllers. And all of them are kind of grouped together in one central place where you log in and you can see all your buildings instead of having to log into each building every time. So BACnet, there's a couple types how BACnet works. So one is and passing, and one is IP, so which is over Ethernet. Now, if it is MSTP, there is a physical wire that goes from the system level controller to the first unitary, to the second, to the third, fourth, fifth, and it's like a big link. And that link is called daisy chaining, okay? And typically what happens is if there's any construction going on, for example, and some contractor comes in and cuts the wire because they didn't pay attention to what was going to happen to the controls, you're going to lose your link where the wire's cut, and you're not going to be able to see anything else on that link moving forward. So then we need to go and fix the wire and bring the link back out. So physically, the sensors, actuators, and all the other stuff land on the unit level controller, and then unit level controllers are all daisy chained together, as we just discussed. So I know this shows a system, but it's still unit level controls we're talking about. So the cooling towers and the pumps may have a controller. The fan VAV box will have a controller. The pump will have a controller. All these are unit level controls. So these controls are programmed in a way that the controller is able to make the equipment work regardless of any input from the system controller as well. We'll go into that again. I don't want to get ahead of myself. So if we have a lot more points than the controller, we can use something called expansion module. So basically just more input and output blocks, which are added to the controller, and it just expands and becomes a bigger controller. That's what it's doing. We'll look into some basic optimization strategies that are being used in the industry. One of them is, and you'll also understand how the controller makes the whole system work. So it'll be a good example. So this is a discharge temperature control loop. So in this scenario, in this air handling unit, we have a discharge air temperature sensor, and which is an input into the controller, and it sends an analog input to the controller. The controller says, okay, I need to increase I need to decrease the temperature because it's too hot and I don't want it this hot. So I'm going to tell this valve to open up, let more water flow through the coil, and that will cause the temperature of air to go down, and we will be able to satisfy space temperature. So that is a classic example of a control loop, very basic and simple control loop. Now we'll keep on building upon that, right? So let's look at the next one, ventilation control loop. So now in this scenario, we are going to take care of the ventilation. Now we've added a couple more sensors. Now we're controlling the outdoor air damper and the return air damper. So in this scenario, we are going to be modulating the outdoor air damper and the return air damper to create a mixed air temperature that we require that will then go through the coil. Then we will detect the temperature. Then we may tell the coil or the valve to open or close based on what we need, and achieve the sequence that way. So far, so good. Great. Now we're going to add an outdoor air temperature sensor. So we'll do something called economizing, or it is also called free cooling. And in scenarios where the temperature outside is nice enough so that you can satisfy space temperature by either just modulating the outdoor air and mixed air, or by tampering the air again a bit. So ideally, you could even use just the outdoor air to cool the space or heat the space, whatever is happening. And if not, you can modulate the controller will modulate the dampers to achieve the desired temperature with the input from the outdoor air. mixed air temperature control loop. Now, we just talked about this, but now we've added a sensor here. It is typically an averaging type sensor because it detects the temperature at various points through this tube, and then sends a signal to the controller where the controller is able to make a better decision on what the temperature is of the air in this space instead of waiting for it to go all the way down in the space and then detect it here. Static pressure. So now we've added a duct static pressure sensor. So we want to make sure if the air handler is serving VAV boxes, for example, and if the VAV boxes are closed, we want to make sure the duct doesn't blow. So we want to put in a duct static pressure sensor to keep a check on that at all points in time. And if we feel, now you see there's a controller and a supply fan, if there's too much static pressure in the duct, the controller can tell the supply fan to turn the speed down, assuming it has a VFD, and make sure that this duct static pressure sensor reading is where we want it to be. And now we'll talk about building pressure. In this scenario, we have an outdoor pressure sensor and an indoor pressure sensor and a relief fan. So sometimes what happens is you're trying to enter a building and then you try to open the door, but the door's so jammed in that you're doing a workout opening the door. Or sometimes it's the opposite, that you go to a building and the door's already trying to blow open all by itself. So what's happening in that building is the pressure is off. Either the building is negatively pressured or positively pressured. If the building is negatively pressured, everything is just being sucked in. So that is when the door won't open when you're trying to enter the building. If the building is positively pressured, so everything is just trying to go out. So like surgery rooms are great examples of positively pressured spaces. So similar thing in this, now there's a pressure sensor inside the building and outside the building to determine the pressure, and we modulate the relief fan to make sure that we always have our pressure readings in a way that it's not too positively or negatively pressured. So again, now system level controls. So we talked about unit level controls where the cooling tower may have a controller, chiller will have a controller, boiler will have a controller, all the other equipment will have a controller. But now at the end of the day, it's great that we have all these standalone controls, but we need everything to work together as one system. So which is why we need the unit system level controls to make sure everything talks together. This is where the logic resides. This is the brain of the system. This is where you typically have the graphics and everything, programming, customized programming, anything of that sort at this level. There is also programming at the unit level controls. So in case they lose connection to the system level controls, they can operate on their own. But system level control may decide to change the set point based on outdoor air temperature, for example, may implement a reset strategy, etc. And we'll dig into that more as the slides progress. So the building is either in occupied mode or unoccupied mode. Occupied mode is when there's people and your building needs to perform accordingly. And unoccupied mode may be an office space that is empty after 5 or 6 p.m. and there's nobody there, so you don't need to maintain the same set points that you would during the day. So major difference, occupied set points versus unoccupied set points. In the occupied mode, as per building code, we need to deliver a minimum amount of fresh air in the building at any given point in time. In an unoccupied mode, that is not necessary, as the building is unoccupied and you can recirculate the air even if it is safe to do so, assuming there's nobody there. Supply fan operates continuously during occupied mode, whereas in the unoccupied mode, it only works as necessary to maintain unoccupied set points. So now Rooftop VAV system. Okay, so we briefly touched on this a few slides ago, but so now, oops, sorry about that. So now there's these VAV terminals that have a controller, and then now the rooftop has a controller as well. So if there were no system controller, the rooftop is told, okay, dump air into the building. So the rooftop is a fan, just keeps pumping air in the building. VAV boxes are going to open and close only based on space temperature. Now, if the space is not satisfied, there's no way for the air handling unit to know when to turn off, when to turn on, if to increase or decrease the speed of the fan without any input from how the VAV boxes are doing. So this system level controllers come in place at that point where it can understand how the VAV is operating. Hey, is the VAV getting enough air even? Is the VAV starving? Is the space satisfied? And if not, if the VAV is starving, for example, it may ask the supply fan to ramp up speed so that the last VAV down the duct that is not the temperature in the room that is not being satisfied, we can change that. Now we'll take an example, similar example for a chiller and fan coil system, whereas there's a dedicated outdoor air unit, there's fan coils, boilers, pumps, chiller. So in this scenario, this is a pretty typical layout over here. A lot of apartment buildings are designed with such systems, whereas typically the fan coil units are in the apartments and they're left standalone, just to give you an idea. But let's do this example where this dedicated outdoor air system in a condo may be supplying air to the corridors on every floor. And the system level controller, there are going to be sensors on the floor. System level controller is going to know when those sensors can change the temperature. It can change the supply air temperature reading of the outdoor air unit based on those temperature readings. If we need an increased temperature inside the fan coil, space is not being satisfied, it'll tell the chiller to kick on or run harder and make sure cool enough water is being supplied to the fan coil units to satisfy space temperature. Or in heating season, it'll tell the boiler to do so, and the pumps are going to work in conjunction with the air-cooled or chiller or the boilers, depending on the system, and it is also going to be controlled by the system level controller. So morning warm-up is an optimization strategy that is used to heat up the space in the morning, for example. So if there's an office building, for example, that gets occupied at 8 a.m., now the system level controller says, okay, it's going to get occupied at 8. So at 6 o'clock, I'm going to turn on the system. I'm just going to close all the outdoor air dampers, and I'm going to recirculate the air and make it hot and make sure that it is good to go before the building opens up at 8. Now, what it notices is that, hey, look, it only took me 1 hour instead of 2 hours yesterday to heat up the building. So instead of 6 a.m. tomorrow, I'm going to start at 7 a.m. And you save that extra hour of energy energy usage. Fan pressure optimization, kind of circling back to our example of when the spaces may be starving. Now, every VAV box has a controller, which is controlling the dampers and understanding what kind of temperature readings is the space that the space needs and what it has to provide. So now it's got a static pressure sensor, it's got a supply fan with VFD, and we've got controllers on the VAV boxes, okay? So now if the space temperature is not being satisfied, this controller is gonna say, okay, I'm gonna open the damper, say 100%, so that more air can go through and the space can be satisfied. Now it opens up 100%, 30 minutes pass by, space temperature is not satisfied. And then what happens is the system understands that the space is starving because The damper is 100% open, temperature is not going up or down depending on what season it is. So it ramps up the supply fan speed and makes sure that the space gets air, this space temperature will start being satisfied, and then the damper will start closing according to the sequence program. Chilled water reset is another optimization strategy where if the load of the building is less than designed, the system level controller can understand the parameters in the building and say, okay, we don't need to run the chiller as hard as we would need to on design, so we'll just increase the temperature of the leaving water temperature and still be able to satisfy the space, hence saving energy. Optimized loop control. Now in this scenario, we're using a cooling tower and heat pump system, where in the first scenario, in the first graph over here, we are running the cooling tower not as hard as you see this red line at the top, and we are running the heat pumps super aggressively. Whereas in the second scenario, we've optimized the control where by running the cooling tower harder than before, we are able to save energy on the heat pumps. So if there's more cold water being dumped into the heat pump loop, you may be able to save energy on the heat pumps from the perspective that they may use that colder water to increase efficiency. Failure recovery. So if there's a chiller plant in a scenario where this chiller is the one that is primary and it fails for some reason, or the cord gets cut, the chiller plant controller is smart enough to know that may not be responding and the chiller has failed, and it will switch over to the next chiller to being used as the primary chiller to make sure that the building gets what it needs in terms of supply water temperature. Similar example with failure recovery. So now in this scenario, we have a heat pump with a thermostat, and it looks like there was some construction and the cord was cut. Now in this scenario, this heat pump, what it's going to do is that the unit level controller is programmed in a way that it is told if you do not have any input from the system level controller, or if you are by yourself, then operate at X, Y, Z parameters. So it is going to start doing that as soon as there's any, as soon as it loses connection to the system controller. Floor plans, we've deviated away from simple floor plans to super sophisticated 3D graphics customized based on mechanical drawings. So typically we would take mechanical drawings from a contractor, from the engineer that the engineer produces, and we'll use those to design the layouts for the floors and use customized graphics to provide for projects. Some of the other things you can do with the system level controller are time of day scheduling. So you can put all your equipment or your systems on a schedule. You can tell, hey, so going back to the same example, hey, the office building's gonna start getting occupied at 8 a.m. So we want to make sure all the equipment is running by then, set points are achieved by then, so we can schedule it that way. It will also show centralized alarms and let you understand what these alarms are, what's causing this alarm, what equipment is causing this alarm, how critical that alarm is. Sometimes you can just get by acknowledging an alarm, or sometimes you need to do major repairs to get things going again. Remote access is something that is very common now with these systems, that everybody almost has remote access. Some of the manufacturers even have apps for your phone where you can log into your BAS system directly. And the BAS systems are capable of generating sophisticated reports that can give you insight into your building and how the energy is being used. And you can take that data and understand how your building performs. There's also a lot of companies that do this as a service. preventative maintenance. So sometimes, depending on the system, you may be able to schedule, hey, let me know after X amount of time to change the filters, stuff like that. Also, it may be able to tell you when to fix your equipment. It's time or it's not time yet. You may also be able to look at stuff like filter status, for example, which is basically just determining the pressure before and after the filter to see if it is clogged or not. And that kind of gives a signal to the controller to let it know. Integrations with other systems is quite interesting as well. As we discussed back in the day, there may have been proprietary protocols used by all companies. And today, now that we've deviated towards BACnet, there's still a lot of buildings out there that are older and still have the legacy systems that are from 50 years ago, if anything, sometimes. So in that scenario, what we do is we try to see if there may be a converter / gateway, whatever you want to call it, that would convert their proprietary communication into BACnet. And that gateway, if it is capable of doing that, then we just connect to that gateway because that's already BACnet, and then we bring it onto our system. So this was the theoretical part of the presentation. I want to know if at this point in time, if there's any questions, and then we can kind of deep dive into an example or two based on how much time we have.
Abhishek, we have 2 questions as of now.
Yeah.
So I think let us take them before we move forward. So meanwhile, we'll give some time to other participants to think of questions as well. So
No problem.
First, from Sumit, it says, why is BACnet preferred over other communication networks in BAS?
So what ended up having was there were a lot of issues, even when we moved away from initial legacy systems towards Modbus and LawnWorks before we eventually got to BACnet. They were better than before, but they were still not quite there where we could say, yes, it is super interoperable. There were still issues integrating one company's LAN into another company's LAN network sometimes. Sometimes it was possible. Like I've worked on projects where we have integrated existing LAN. Sometimes also what happens is there may be a new BACnet controller that may be able to talk both BACnet and LAN, and you may be able to integrate some existing LAN devices in a building into a newer BACnet front end. Does that answer your question though? Before I deviate away too much from communication protocols.
I think the person who has asked the question hasn't said anything, so we'll take it as a yes.
Okay.
So the next question, he says to some extent. So maybe if you can elaborate it and we can take it in the end again. The other question is coming from Surender. I'm not sure, however, which controller he's referring to, but he says, can we VFD drive be with one controller?
Can we control what?
A VFD drive with a controller?
Yeah. So a VFD drive would go, for example, on I don't know, a pump or a fan. So now instead, so if you were to, so let's take an example for a fan. It'll be the same control point, but so now if you've got fan, you've got on off. So if there were no VFD, you would just have on off, alarm, and feedback. Okay, so you've added 3 new control points by adding a VFD. Feedback, alarm, and speed. Does that make sense?
Yeah, I think so. Let's take one more now, and then we can wait for later. The next question is from Daniel, who asked, can VFD be a unit control?
100%. So now, if you have a air handler, I'll just take that again, same example. if you have an air handler in a building that does not have a centralized automation system, you can just put in a unit level controller and tell it to do X, Y, and Z based on the input from the thermostat. So it can be a unit level control. And you would still have the same 5 points for the VFD. You would still program the controller the same way. Now, the only difference is that this controller is not going to get any external input from the system level controller if there's anything else going on in the building. So it's just got blinders on. It's told to do one thing, and that's all it's going to do.
Sure, makes sense. So I think let's continue with the session, and maybe in a few minutes again we can switch to questions.
Can I have one more question, please?
Of course.
We'll switch to questions because we are going orderly. Please type your questions in the chat box and we'll take them progressively. Please
The
type.
question is quite lengthy. That's the problem.
Abhishek, what do you want to do?
No problem. We can address the question.
Okay. Let's take the question.
So my question is, I have a multiple VAVs inside the building with an air handler having VFD. Okay. So the normal control strategy will be control as and when the VAVs are getting open and closed, the static pressure in the duct getting changed, and accordingly we will be controlling the VFD. The air handler fan using VFD.
Right.
So instead of why can't we integrate all the VAVs through backnet network and control the VFD based on the air requirement? Which strategy would be better? Either the first one or the second one?
So sorry, just to reiterate, the first strategy is controlling based on pressure, and second strategy is controlling based on temperature. Am I understanding this correctly?
Yes, exactly.
Okay,
by
I think
soft integration.
By what?
By soft integration through backnet.
Okay, so in this scenario, your VFD, your air handler is coming with a backnet controller?
Yes.
Okay, so it's coming with a backnet controller. Your VAVs are coming with a backnet controller. So the quote unquote soft integration would, I would say, technically your VAV would have a physical controller on it, regardless, which would be wired up to the VAV box points.
Yes.
So now those controllers are going to be physically connected, depending on maybe it's a wireless solution, but for the sake of this conversation, let's assume that it is a wired solution. So the link will go, and you're saying there is a system level controller. I assume that's how you're going to control it as a system. So now in this scenario, it actually needs, in my opinion, at least, it needs to be controlled on both temperature and pressure, because temperature is going to make sure that how you can control your valve and how the VAV box is going to operate. The air handler is going to operate, and the pressure is going to make sure that the duct is in good shape, so you can ramp up and down the VFD based on if the space is starving or not, and you may also be able to see energy savings that way.
Okay.
Does that make sense?
Yeah, it makes sense, because in the first strategy, normally what happens is that when we have a remote VAV in the remote end of the deck, then the control will not be perfect.
Abhishek, I think we only have so much time for this question. I'm sorry, we can take it offline.
Okay, no problem.
We have a time limit of 6:30 and we need to take other questions as well. So I think, Abhishek, we can continue with the presentations and switch to questions later.
Okay. So we'll do a sample project, and it may answer some of the other questions as well. So I just kind of made this up as I went along. So there's an office space in this example which has 2 rooftop units. 2 of them come with backnet controllers. 2 of them come with existing. So in this scenario, this is an existing building. So these 2 rooftop units are existing, and they have legacy controllers. You've got 15 VAV boxes in the building, and seems like there's perimeter heating. So it looks like they're supplementing the cooling only VAV boxes with the perimeter heating in this scenario. You've got boilers and pumps. There's a humidifier. There's some motorized valves and dampers. seems like there's a domestic hot water as well. So in this scenario, here's what we want to see. So if I'm a controls contractor looking at this project, I look at the two backnet controller, the two new rooftops that are coming with backnet controller. So from that perspective, I know that I don't need to account for physically hardwiring a controller to the terminal strip of the rooftop unit. All I need to do is run communication wiring to the rooftop unit, and I'm going to be able to see that rooftop as a device on the front end of the system controller. Legacy controllers, I need to understand either if the manufacturer has a converter that's going to convert their legacy protocol into backnet. If yes, I'm going to buy that converter and use that converter to point map into my new system. If they do not have such a thing, then what we may want to do is just put a controller, wire it to the terminal strip of that unit, and you may just get the simple 5 wires of the thermostat control and be able to control that unit that way. VAV boxes. Now, each VAV box is going to need its own controller. Technically, so does perimeter heating, but what may happen is if it is being used as supplementary with the VAV boxes, it is going to be in the same zone. So we may be able to use one point on the VAV box to send a command to the perimeter heating valves to open up or close up, depending on what we need to do in the space. Sometimes, most of the times, you're able to find that one analog output or binary output, depending on what kind of control signal is required. But if not, then you can put on a little expansion module onto the VAV controller and just wire it up to that valve over there. Boilers and pumps, same way. Boilers typically end up coming so typically boilers would be proprietary or Modbus even in some cases, and they talk Modbus amongst themselves, for example, and then it may have like a backnet card that you are able to pick up. If that is the case, then all you're really doing, and you may need to look into providing a controller, hardwiring all the points as required to program whatever you need to program, and integrate it that way. Now, same thing, if these pumps have VFD, then you need to account for those VFD pumps as well. Sometimes VFDs come with backnet as well, IP or MSTP, depending on the manufacturer, and we need to account for integrating those points at the same time. Humidifier, it's gonna be the same thing. Either it's gonna come with a backnet card or not. If yes, then communication wiring only. If not, then we need to see what points we can pick up. At least we're gonna try to pick up start, stop, and status at least. Motorized valves and dampers. So now again, we talked about how to control these. It's an analog or a binary output that you're sending to the actuator of the valve or the damper, depending on what it is. So we need to account for that. Sometimes these dampers are massive. So what may happen is the manufacturer is going to break it down into little pieces and ship it to site. Now, in that scenario, you may have more than one actuator per damper, and you need to account for those extra points as well. Domestic hot water, typically it can be a standalone, it can be a 24/7 system because we need domestic hot water at any given point in time during the building. And sometimes if it's on the BAS, it may have some safeties. If the water gets too hot, it'll stop. And there's storage tanks as well to keep the hot water in there. I think that finishes like the first sample project. Does that make sense? Any questions? Or I guess we're gonna do questions at the end. So I'll go.
Or we can take another. We can take another one question, Abhishek.
Sure.
So what we'll be taking questions through text, so that it's organized.
No problem.
And so the next question comes from Vinay. He asks, is IP-based system, the cost of IP-based system lesser than conventional BAS system? And if yes, what would be the percentage of incremental cost?
Will it be less? It could possibly be.
It costs much higher. I read less. It costs much higher.
It costs. I mean, here's the thing. So in an IP-based system, in an MSTP-based system, you have the physical link going from the controller to controller to controller. In IP-based system, you don't have like that one link per se, but now you need to get IT involved so we can have Ethernet drops, or sometimes depending on how the job goes, it may come in your scope. But basically, the IT will be heavily involved because their system is going to get super clogged by all the data that is flowing through. Now, when I say super clogged, it's not to a point where they can't do anything. It's just a lot more data than they're normally used to seeing, because now the BAS data is also on the same building LAN. So it's more from that perspective on how the IT department perceives it as well. A bunch of the manufacturers have started moving towards IP-based systems. So their controllers are completely IP-based, backnet over IP. So they're doing all their projects that way. I wouldn't say it is a significant more or less versus it really depends. I hate to say this answer, but it really depends on the project and how long you have to do the runs, etc. So it would go by project basis in terms of cost, because then that would come to the electrical subcontractor that the controls contractors typically hire to do all the wiring in the project, and they would be the ones running the Cat5 cables around the building.
Sure, makes sense. We can continue, I guess.
Okay. So we'll do a second sample project. In this scenario, it is a multi-res building. There is heat pumps and ERVs in the suites, and there's some amenity heat pumps, cooling tower systems, boiler plant, pumps, makeup airs, motorized valves and dampers, irrigation system. Okay, so let's go through them one by one. Heat pumps and ERVs, typically in multi-res buildings over here at least, they don't end up putting controllers in every unit. So they typically leave those standalone. In some cases, we do end up doing that depending on what the developer wants. Typically, what happens in condo buildings is they let it be on its own. So in this scenario, if we assume that then the heat pump is going to have its own standalone thermostat inside the residential suite. If it does not, then it has a controller and the thermostat is wired to the controller. And there's ERVs that are typically for the bathroom exhausts. They are just on like a 30, 60, 90 or 10, 20, 30 timer switch. There's amenity heat pumps. Now in this scenario, in an apartment building, there are amenity areas. There may be some office conference rooms, for example. There may be a gym. There may be a spa, etc. So all of these things are being served by amenities. The heat pumps and the amenities, these are typically horizontal heat pumps. They will have a backnet controller on them, either from the manufacturer or will be installed in the field by the controls contractor. And there will be a thermostat wired to this controller. Sorry. Similar thing with the cooling tower system. Sometimes what may end up happening is the manufacturer may supply a control system depending on how the spec is, or like a controller for the cooling tower, depending on how the spec is written. And if that is the case, then the controls contractor would go and wire up all the points to that controller and install that controller. And if that is not the case, then we would still wire up the points, but now in this scenario, we will provide a controller at the same time. Boiler plants, same thing. We just talked about the boiler plant in the previous example, depending on if it is coming with a backnet card or not. we may integrate it in that fashion. And if it's not, then we may need to provide a controller and wire up all the points. Same thing with the pumps, depending on if the pump has a VFD or not, 2 points versus the 5 points we discussed in the previous example and in the question. Makeup air units, we've got, depending on the unit, coming with BACnet card or just a terminal strip, we may need to put on a controller, hardware all the points, field install all the sensors that are being shipped loose by factory, and motorized valves and dampers, same thing, analog output versus binary output. If there's a feedback, then we need to account for that point as well. That tells us if we've told the actuator to open up X percentage, then it tells us that this is what percentage the actuator has ended up opening at. In this scenario, there's an irrigation system as well, and it seems like it's coming with BACnet. So what we would do in this scenario is maybe wire up some, when I say wiring that we do, we as controls contractors, 24 volts is the wiring that we touch, typically 120 volts, which is the high voltage. And I know in India it's 240 volts. So the high voltage stuff is done by Division 16, which is the electrical contractor on the job. And exhaust fans, the same thing, depending on if sometimes it's just interlocked with the makeup air, sometimes it may have a controller, it may on off and status, or if it has a VFD, then it may have on off status and the other VFD point. So I believe with that, I am done with my presentation. I don't know what these yellow lines are, but I'll take any other questions at this point.
Great. So we have a couple of other questions as I can see on the screen before we wind up. One question, what all is included in the DDC control of an HVAC system? This is asked by Swapnil Jain.
What all is included?
In the DDC control of an HVAC system. I don't really, even I don't understand the question. Do you?
I mean, if this is a control system, this is an HVAC control system for an office building. It needs to, there's a centralized controller and there's unit level controllers. So the system level controllers is where the programming resides. And like, does that answer the question? Or are you looking?
I think it does. I think it does. It does.
Like, if you want to take it one, if you want to take it one step deeper on a unit level controller, you need current sensors and relays to. Relay is going to be used to turn on and off whatever device they pump, for example, and the current sensor is going to tell you the reading for the status. If there's an end switch on the actuator, you'll get the feedback. I don't know. Does that answer the question?
Right, yeah, it does. It does. I think it does pretty much. There are a couple of elaboration questions which we'll get to later. There's one other question which is significantly interesting to me. It says, sir, could you please touch upon a few best control strategies for residential and commercial building? This is asked by Vinayak Sudalai.
So I would say to refer back to these strategies that we talked about, because these are best practices that happen in the industry today. So pressure control loops, temperature control loops, economizer control loops. Economizing is something that saves a lot of energy. Now, again, there may be some difference between how the mechanical systems designed in India versus how they may be designed here, because the weather conditions are very extreme in both parts, actually. Even North India versus South India gets pretty extreme as well. So depending on that, you may want to program your economizer control loop accordingly, and you may want to change different set points, basically. And that is the variable that you use to control your building based on what part of the world you're geographically located in. So I would say refer back to these control loops and try to see how you can implement some of this in your existing projects. So what you need to do is account for some of these sensors in your product spec of the equipment. So if you want the equipment to come with a discharger sensor, you better specify that in the spec, so that when the project goes out for tender and when it's awarded, the controls contractor is going to carry that sensor, or the manufacturer is going to supply that sensor. Typically, it's something that will come loose, and the controls contractor will go and install that loose sensor as well, and then program the sequence based on what you specify in these control strategies.
Great. We'll take one last question, because this webinar is only a 1 hour session. The last question is coming from Mohammed Ibrahim, who is the RVC RAL of membership promotion. He's from Falcon Chapter in Dubai. He asked, what is your opinion using industrial PLC instead of VMS for large cooling plants and district cooling?
See, typically what it is that, so say if you're in the Middle East, I know there's an extensive cooling need out there. PLCs are typically something that are used in process automation, something that is very, very critical. So now if a large manufacturer of anything doesn't need to be even relevant to automation in this case, it has a manufacturing line where something is being made, anything, it could be anything. Now, if that manufacturing line stops, that manufacturer is going to be losing money per second, and it's going to be a lot of money that they're going to be losing every minute that line is down. So critical, super critical processes like that is what typically we see PLCs being used in. Typically in HVAC projects, these are not very mission critical systems. These are way, way, way slower response time than PLCs. So it could take, I don't know, like if it takes 15-20 minutes for the space temperature to change, it's not going to make much of a difference. But if the line is down 20 minutes for 5 times, that's going to make a lot of difference. So going back to your scenario of using PLCs in district cooling, I would say it depends on how critical your environment is, and if it is very critical in a very large plant, then you may look into using PLCs in that scenario.
Great. I think that answers Muhammad's question. With this, thank you so much, Abhishek. I would like to hand over the control to Mani Khanna, who is the Secretary and CTC Chair for the ASHRAE Chandigarh Chapter, to finally conclude the session. Mani, please take it over.
Yeah, thank you, Kushal. So now you can change your screen, Abhishek, please.
Okay, I've stopped sharing now.
Yeah. Yeah. So thank you everyone for all of your participation today in this great webinar, which was organized by ASHRAE Chandigarh Chapter and ASHRAE Rajasthan Chapter jointly. And it is a great initiative which we have taken for imparting knowledge during this critical time when everyone is at home, and when we all get together and share some knowledge regarding the prestigious topic. And once again, we would like to thank you all for your participation. And again, would like to thank Mr. Abhishek Khurana, who is a great speaker from Toronto, and he has given a good presentation related to the topic. And everyone is appreciating in this chat window so the great webinar and great knowledge he is imparting to the participants. So again, yes, it was a houseful session, and many of the people were not able to join because of the maximum capacity of the webinar. And we would also like to thank Mr. Ashu Gupta, who has connected us with this speaker. And by this, we would try to hold this webinar today. And also would like to thank many of the participants who have joined from various chapters related to Rajasthan, ASHRAE India chapter, ASHRAE Deccan chapter, ASHRAE Pune chapter. So many of the participants are being attended. And from ASHRAE Chandigarh chapter, so many senior people have been joined, Shri P.S. Saniji, Swapnil, Prabhakar Jha, and many of the people who have been joined this today's webinar. So again, please keep in touch, and we'll definitely arrange many of the webinars in the upcoming series. And we are running a series of webinars this time, which would be organized by ASHRAE Chandigarh in jointly with the some other chapters. And again, thanks to Anuj, who have been created this link and provided the technical support for this webinar. And our next webinar is on 17th of April 2020, which is again at same time 5:30. The topic of which is Introduction to ASHRAE Certifications. So see you there, and let's connect. And yes, definitely this webinar will be uploaded on the YouTube channel of ASHRAE Chandigarh chapter, and the emails can be forwarded to ASHRAE Chandigarh and ASHRAE Rajasthan chapter, who will provide you the support after connecting with the speakers for relevant questions. Will provide you the response definitely, right? So thank you very much for all of you for joining today this webinar.
Thank
Thank
you
you,
very
Abhishek
much.
ji.
Thank you,
Thanks.
Abhishek.
Everybody.
Thank you.
Thanks.